Welcome back, and today we will continue from where we left off in the last lecture. We are still discussing, and we will probably keep discussing for next few lectures, thermal design, thermal management and cooling technologies. Okay. So, in the last class, if you recall, we discussed thermal resistances. Okay. And during that we looked at bare die architecture, we looked at integrated heat spreader architecture, package architectures, that is. And in all these cases we were looking at something called a heat sink. It is a cooling solution. So, what is a heat sink, and therefore, what are the different cooling solutions that we will talk about? We are going to look at that in this lecture. Okay. So, the concepts that we are going to cover today, we will take a small slide, of just a single slide on cooling hierarchy, and then we will start with heat sink. Okay. So, let us move on. So, this is cooling solution hierarchy. See, you have a piece of silicon, and then you put it in a package, which is the first level packaging that we talked about, and then this package goes into a motherboard. So, it is first level, second level all together, and then we put a thermal solution which can take various forms. We are going to look at all those, the thermal solutions. That is what thermal engineers do, and then this thermal solution goes into the overall system. And within the system, depending on the number of microprocessors that needs to be cooled, there can be multiple thermal solutions. Now, the one thing I would say is, during this entire discussion on thermal design and management, we are going to focus on computing products, okay, laptops, desktops, tablets. Okay. But that being said, it may be most of the principles, the philosophies, many of the technologies that we are going to talk about can be easily applicable and also are applied in various other products as well. Okay. Various other electronic products, in telecom products, okay, in battery management, BMS, battery management systems, so on and so forth, okay, or even appliances like TVs, consumer appliances, okay, consumer electronics, I will say. All right. So, let us move on, and this is the cooling solution hierarchy. So, a typical thermal management solution in a computing product looks like this. In case of a desktop, and you may have had the experience, if you have ever opened the desktop chassis, you may have seen this. On the piece of silicon, you will see a fan, and you will see something that looks like this. Okay, it is a base with some metal plates coming out, extruded to the base and coming out in the normal to the base in the form of an array. So, that is called a heat sink, finned heat sink. Okay. And the fins can be straight, fins can be curved. The fan actually can be at the top, fan can be blowing from one end. So, all these configurations are possible, and this is called a fan heat sink combination. Actually, if you go to any of these e-commerce sites like in India, Flipkart, Amazon, you can actually order many of these. And what I will try to do is, in the next lecture, I will try to bring some of these actual samples and show it to you. Okay. In the notebook system, however, what we have is something called a heat pipe. So, here also you see a fan and a heat sink. This is actually a heat sink, probably not very clear from here, but these are actually these are plates one after the other. Okay. It is an array of plates one after the other, and the fan blows air through this fin array. So, this is also a fan heat sink arrangement, but unfortunately this fan heat sink is too large to be placed directly on the piece of silicon, directly on the CPU. So, therefore, what is done is, we use a cooling solution, a cooling technology called heat pipe. So, you have the silicon, you have a thermal interface material, you have a copper plate, and then within the copper plate we embed something called a heat pipe, which on the other end is connected to this heat sink through which the fan is blowing the air. So, what happens is, this heat pipe actually conducts the heat or transfers the heat, transports the heat that is generated at this location, at the location of the silicon, very efficiently from this location to that location, from the silicon, which is the hot junction, to the heat sink, which is where it is cooled. Okay. So, at this point let us, so it looks like a rod of copper rod, but actually it is something called a heat pipe, and we will see what a heat pipe is, how it works, and so on, what is inside, so on and so forth. Okay. But what I am trying to say over here is, in a notebooks or basically a laptop system, this is a very common cooling solution. All right. This is in a laptop it is not possible to keep the fan and heat sink on the CPU directly, because the amount of space that is available at the location of the CPU is too small, especially in the height, because you have a very thin box and the motherboard runs in between, on top of which is the CPU, sometimes on the bottom also can be, but mostly at the top. And so, you have only a few millimeters that is left, but the fan and heat sink that you need for cooling needs to be much thicker and larger. So, therefore, you take it outside the motherboard footprint and look and use that, you place the heat sink and the fan in a location which is outside the footprint of the motherboard. But then how do I transport the heat which is generated at location A to location B? Heat pipe is one of the most efficient techniques for that. We will see how it works. All right. So, now before we go to heat sink, we will just spend one slide on what is called fins and what is the advantage of having heat transfer using a fin. Okay. So, again, people who have taken undergraduate heat transfer under mechanical engineering, this is something very familiar to you. So, fins are appendages, let us say, that is attached to a surface so that it increases its surface area. If you look at a fish, for example, fish has fins, it is an appendage, extended surface area protruding out of its body. So, for in the nomenclature of heat transfer and heat sink, this is how a fin looks. Let us say I start with a hot plate placed in a colder ambient. The heat transfer coefficient is H, the plate is at a temperature Tb, and I will say why B, why not plate for P or surface for S, or S for surface, P for plate. I will talk about that. But in such a scenario, if the area of this plate is A, then what is the amount of heat transfer? H A Tb minus T infinity. Agree? That is what it is, Newton's law of cooling. And let us say this is not enough. I put just a copper plate, and you do this, and you find that the amount of heat that you can dissipate is not enough. Okay. So, one is you go back to the electrical designer and say, boss, not possible, I cannot cool this much. And then he will ask, did you try, did you think of other methods? Okay. So, it is better we do it ourselves in the beginning. So, what can we do? So, then one of the most common ways is to, okay, I have this plate and I take another rectangular plate and attach it in a direction normal to the surface in this manner. Okay. So, this becomes a fin because this is protruding out of this surface, it is like an appendage protruding out of this surface. And for a moment let us assume that this is a perfect contact. You add another one like this and you keep adding one after the other as much as this can permit. And once again, even though this slide tends to show that the thickness of this plate and the thickness of the fin is the same, it does not necessarily have to be that. In fact, in many cases the base is much thicker than the thickness of the fin. All right. So, therefore, what happens? I increase the amount of surface area that is available for heat transfer. Earlier it was, now if you look at this, you have the fins and you have the base of the fin. Earlier you had just the base only. Now you understand why I use the subscript B for this, because finally this becomes the base of the heat sink. This is where the heater is attached. This is what is placed on the CPU, which is the heat source. Okay. So, therefore, Now, I have increased the surface area. So, what should it be? What should be my total heat transfer then? You can say Q, sorry, we can write then Q is therefore H times area of the base plus area of the fin times the number of fins, correct, and then times Tb minus T infinity. I can write this, and you can see that since my area has gone up, the amount of heat that I can dissipate also goes up. Okay. However, the problem is I cannot write like this. So, this expression is actually not correct. The correct expression is actually what is shown at the bottom over here. A total is area base plus number of fins times area fin, but there is something at a multiplier denoted by eta, and eta is actually called, I am sorry, what happened? This eta is actually called the fin efficiency. And it typically lies between 0 and 1. Now, what is fin efficiency, or why does it come? Because why does the heat get, how does it help us in heat transfer? Earlier it was completely by convection, but now what happens is part of the heat gets conducted through this surface and then gets convected out, right, or then gets lost by convection from these lateral surfaces, and then whatever is the exposed base area still participates in the convection heat transfer. All right. So, many a times typically you would say, well, I should subtract the thickness of the fins from the base. Yes, of course you should, but then also keep in mind that you have the thickness at the top as well. So, anyway, one can come up with a lot of more accurate versions of this, but this is more or less widely used. Area of the base plus number of fins times area of each fin times the fin efficiency. Now, why does fin efficiency arise? Fin efficiency arises because the entire fin, remember the heat is getting conducted through here. So, it is getting conducted and in the process it is also getting lost from this surface by convection, clear. So, therefore, what happens is if I measure the temperature from the base to the tip, I would see that the temperature actually, if I measure the temperature along the length of the fin, I would see the temperature actually undergoes a drop. So, therefore, the entire fin is not at the base temperature, and since it is not at the base temperature, I cannot use Tb minus T infinity for this entire area, clear. So, therefore, what we do is there is a complicated calculation which gives us this expression for the efficiency, which is defined as the actual heat transfer divided by the heat transfer which we would have got had the entire fin been at the base temperature, but in reality it is not going to be that. Okay. And we will see that that depends on a variety of parameters. It depends on the overall heat transfer coefficient H, it depends on the conductivity of the material as well as the geometry of the fin. Okay. So, we are not going to get into the details of that. If required, you can look up any heat transfer book, and this is a very basic chapter in conduction. but the overall area goes up. It is not absolutely directly the fin area that is added to the base area. There is a multiplier which is less than 1 given by fin efficiency, but overall there is a significant increase in surface area and therefore overall heat transfer. And if we talk about thermal resistance, fins increase surface area, thus reducing the convection resistance 1 over H A, because the A now is becoming higher, larger. Clear? So, later on what we will do is, we will probably spend at least one lecture if not more in solving some typical problems, and over there I will give you some expressions to calculate this fin heat transfer or fin efficiency rather. All right. Okay. So, now let us move on and let us look at, so when you have a number of these fins attached one after the other, we get a heat sink. All right. So, on the right hand side, on the left hand side, we see a base and fins attached to it in the form of a parallel plates. It is called a parallel plate heat sink. Many people call it longitudinal fin heat sink. All right. And air will flow through these passages between the adjacent fins, and while passing through, it is going to extract the heat from each of these surfaces as well as the base. Now, instead of a continuous longitudinal plate like this, we can also have pins in this form. So, this is called a pin fin heat sink. Okay. So, a pin fin heat sink has its advantages in the sense we are not going to get into those details, but it does increase the mixing of air. It is not a smooth flow between in a channel, but now the air flow becomes a little chaotic, and which actually helps in increasing the heat transfer coefficient. Okay. But however, it also increases something called a pressure drop or flow resistance. We are going to talk about that later, and that also we have to keep in mind. So, there is an advantage, there is a disadvantage, and any problem in life actually is an optimization problem, and so heat sink design is nothing different. Okay. So, heat sink design, what will it depend on? It is just the heat sink design. I am not even talking about airflow and all. It is going to depend on fin profile, fin height, fin length. Length means in the direction of the airflow, height means quite evidently it is the height which is in the direction away from the base plate. Fin profile, what does it mean? Well, it can be longitudinal fin, it can be pin fins. It can also be trapezoidal fin. It does not have to be absolutely a rectangular cross section. It can be circular cross section, it can be annular fins, so on and so forth. So, fin profile also does play a role. It can be thick at the base and then go up. Okay. So, what I am trying to say is the fin profile, instead of being like this, can be like this. In 3D, it can be in the form of a cone, truncated cone, instead of a pin fin that I have added, I have drawn over here. Sorry, please excuse my drawing, it is very bad, I know, but this pen I am not very very comfortable with this, so it shakes, but I hope you get the idea. Okay. So, now and finally, base plate thickness, fin density, how close are these? Okay, that depends, that actually has a very important role in actually determining what is the heat transfer coefficient. When you place fins very close to each other, then the heat transfer coefficient may go down or the pressure drop may go up. For a given flow rate, pressure drop may go up, or for a given pumping power, velocity may go down if it is forced convection. Okay. But and the heat transfer coefficient as a result may go down. We will see all these later. But then you have more number of fins means more surface area. So, what is good? Higher H, okay, that is one. Higher A is the other. When you have two dense fins, effective heat transfer coefficient may come down, area may go up. Now, which one comes down and goes up by what amount will determine whether the final heat dissipation, which is H times A times delta T, the heat dissipation rate, whether it increases or reduces or remains the same. Okay. So, these are all important. So, fin density is very important, and material, of course. If it's copper or a very good, or aluminum, you will see that for most geometries the fin efficiency is going to be very high, 90% or higher, sometimes very close to 1 for copper. But if you use plastic fins, fin efficiency is going to be very low, because the conduction through the fin is going to be very inefficient, and most of it is going to be lost by convection very close to the base itself. So, the tip temperature is going to be very, very much lower compared to the base temperature. So, fin efficiency therefore is going to be low, okay. And therefore, the total area, effective area, is also going to be low, because A total was A base plus fin efficiency times the fin area times the number of fins. Okay. So, let us look at some heat sink types. So, these are heat sinks. You see several configurations. I am showing these pictures. I want to acknowledge Intel Corporation, my first employer, from whom I got these pictures, from where I got these pictures, I would say. And you see these are finned heat sinks. So, the actually the base, this is a circular base which sits on the CPU or the heat spreader, and then you have a fan that blows the air radially outwards through these fins. This is the configuration. Look at this one. This is like a typical parallel plate longitudinal finned heat sink, right. You have the fan on the top. That fan blows the air in the downward direction, and the air, once it comes down, impinges on the base and then comes out from both sides through the of the fins, okay, from this side as well as from the other side. Okay. So, the air comes down and then goes out from either side. Same over here, except what you see is these fins are curved, just like many people call it skived fins. Instead of rising straight, it is curved. How does it help us? If your total height, the space available in the vertical direction is limited, then if you curve the fin a little bit in the way it is shown in this picture, you imagine the effective length of each fin is higher, and therefore, effective surface area is also higher. Yeah. Effective surface area, or total surface area, total effective surface area of the heat sink is higher, right. Okay. So, these are called active fins. Why? Because these come integrated with the fans, and the act is active because the fan has to be powered on. You have to supply power, hence it is active. If there is no fan attached and it is just a heat sink, it is called passive heat sink, and you see some examples over here as well. The heat sink by itself comes as a passive device. Then you can either just put it and you will only have natural convection, or you can have a fan externally attached to this heat sink, either blowing directly into the base, which is called impingement mode, which is what we saw over here, or you can have a fan placed at one end, which is blowing the air from one end to the other along the channel, which is many a times called the flow through mode. Okay. This one, you see, this is called a folded fin. The fin is like this, as you can see, goes up, gets folded at the top, comes down, and then it is attached to the base somehow. This one, the flow is channelized. The top is actually for both of these, you have cover at the top, so that the flow is channelized. So, if there is a flow through this, it does not enter and then escape from the top. It will be forced to flow like a channel covered on all four sides. Okay. Whereas, this picture that I was showing, as the air comes, it may end up flowing through the channel from this end to that end, but part of it may also escape from the top if I do not cover it. Clear? So, I mean, lot of variations possible, lot of things possible. Okay. So, that is what I wanted to cover here. I wanted to give you in this lecture a feel of what a heat sink is and how a heat sink is designed, what is the fin, how does it help, And why a finned heatsink is so popular? See, we are talking about only in as heat sinks in electronics cooling, but these fins, you can see it in a multitude of applications everywhere. The most common one is your car radiator. Look at the car radiator, you have these fins placed right next to each other, and except that you do not have a heated base, instead what you have is you have these tubes through which the coolant is passed or the fluid is passed. Okay. You open your air conditioner, if it's a split AC, with the evaporator inside, that the inside indoor unit, if you just open the lid, which is very easy to open actually, there are two press points at the sides. If you open, the front lid goes up. If you ever seen a service technician, you will see this, and inside you will see all these pipes and these fins attached to the pipe. These are called finned heat exchangers. Through the pipe is what your refrigerant flows, okay, the refrigerant vapor, and the air actually flows through the passages between the fins, and as it flows over the tubes through these finned passages, it loses heat to the refrigerant, and that is flowing through the tubes, and therefore what we get indoors, what we get inside the room is cooled air or chilled air. Okay. And the same thing is on the other side, which is called the condenser side, all right, where you have a fan blowing ambient air, and which actually takes the heat away from the refrigerant and throws it, if I may call it so, colloquially using, or rather more technically dissipates it to the ambient. So, finned heat sink or finned heat exchangers, or the concept of fins as extended surfaces for enhanced heat transfer, is extremely popular and used. I think if you just look around, you will see examples of finned heat sinks or heat exchangers, and our application of electronic packaging and electronic cooling is no different. Okay. But many a times what we will see is, okay, that heat sink, just a fan heat sink combination may not be enough, we have to do something else, and especially at the location where you may not have adequate space to put a heat sink and fan of the required size. So, all these constraints do come, and we will see examples of those in some of the subsequent lectures. Okay. So, thank you very much, that is all I had, and in the next lecture we will continue our discussion on finned heat sink, and we will primarily look at that given an application, how do I determine what is going to be the performance of a finned heat sink. Thank you very much.